Welcome back. We are now working in chapter 3 of the linear algebra book, starting to get into the 4 fundamental spaces within linear algebra. What we'll end up finding these spaces to be is the column space, the null space, and then we start looking at A transpose. So the null space of A transpose, and then the column space of A transpose, and digging into those spaces, column space, row space, null space, and then null space of A transpose as the 4. Now before we do that though, in this very first section, what we're going to kind of define and start to look at is really, what is a vector space before we start diving into the specific ones, as well as what it means to be in a subspace. If you've taken any kind of discrete mathematics course, typically discrete mathematics is an advanced level, tend to take after linear algebra. You may take during linear algebra if you're in college. Here at Mount Vernon, we offer discrete as an option that you can take after Algebra 2. It's kind of a logic, discrete kind of course. And so if you've taken that before this, then this subspace phrase should be really, really familiar because we look at subsets, and vector spaces and subspaces are very, very similar to sets and subsets and how we look at it. The definitions, though, have to be a little bit more specific. And so to help kind of define what that is, when we talk about vector spaces, the primary vector spaces that we will be working in are of the Rn, so R1, R2, R3, all the way out to Rn. And when we look at these vector spaces, specifically up to Rn, what we're looking at are all of the vectors in these spaces. And so when we really think about space, and I kind of noticed this when looking through the textbook, is there's never a formal definition for this. The best way that I can think to kind of describe it is if you were to consider your room that you are sitting in, everything that takes place in that room, any kind of action that takes place in that room, as long as it stays in that room, we could essentially refer to your room as a space. And then any individual actions, things that we could look at, we can then start to define that as a subspace, something that you can do within that room that still keeps you in that room. And so it's a very, very similar idea here with vectors. And so these are our primary vector spaces. Now, if we begin to include complex numbers, then these vector spaces can change to the notation with the C for the set of complex numbers, or ultimately the set of complex vectors. We have not really looked too much at this, but because we know how to add and multiply with vectors and i's, we can fit this right on in terms of looking at those spaces. We have already kind of talked about the column space without really formally defining it as a vector space, but this is a subspace of the reals, R2, R3, R4, etc. But it is another idea. Remember, this was all of the linear combinations of the columns for a matrix. And so when we start to look at all of those different types of combinations, that space that those combinations fill is a vector space in terms of that definition. And so this is actually another example. It's one of the fundamentals that we've already seen a lot. But the idea here, I think that's really helpful, and that I mentioned a second ago, is when we're talking about a space, we're looking at linear combinations of those vectors. And to be defined as a space mathematically, it has to follow a certain set of rules or axioms. In the textbook, if you're using it, he mentions this at the beginning, but those are listed. Actually, there's 8 total rules at the beginning of problem set 3.1. I was just going to grab my water. That must be satisfied for your vectors to be qualified as a vector space. And so he mentions you don't need to memorize these. I would encourage you not to memorize these as well, because what's really nice is when we start breaking this down into just the linear combination of a scalar times my vector plus another scalar d times another vector, when I do this linear combination, the results that I get from here have to stay within that space. And if that is true, then those 8 rules are satisfied. But there's one little caveat that we have to make sure happens, and that is that we need the 0 vector to exist within this space, because what if, for example, we were able to take CV and subtract from it CV, then 0 has to be in that vector space. We cannot have a vector space without this 0 or the origin included. Which is kind of what I wanted to point out when he, in the textbook, gets into some things that are not a vector space. He mentions all of the vectors whose components are strictly positive. So like if we were to list out the set of all vectors, v1, v2, v3, all the way out to vn, making sure I'm kind of following in suit with this. If vi is greater than 0, this is not a vector space. And the reason why it's not a vector space, just immediately, is that if all of these are supposed to be strictly positive, I'm supposed to be closed under multiplication. In other words, I should be able to multiply any vector in this set and stay within this set. Well, if C is negative, multiplying this by a negative number, if these are all strictly positive, is going to result in a vector that has negatives, which isn't allowed. So this cannot be a space. He offers up the idea later that when he gives some examples of vector spaces, that it doesn't have to just be vectors, but we can look at matrices. So if I had a matrix, an m by m, or an n by n, just a square matrix here, that if this was, say, we're going to look it up or triangular later, but let's just say all of the entries are the same. So if this turned out to be A, if I was to multiply this by any constant, then this would stay the same in terms of all my entries. If I add another matrix in this set, it would still stay in terms of everything being the same, no matter what I do. And if A was 0, then the 0 is included. So like this would be an example of a vector space. So specifically a matrix that's n by n, so a square matrix in this case, where every entry is the same, this would create a vector space. Now, what's really interesting with this, and this will get defined a little bit later as well, is this specific type of matrix we can actually refer to as a subspace. Specifically of any matrix that's m by n. So because this is a specific type of matrix, it itself creates a space, but this is within the overall grand scheme of every 2 by 2 matrix. So that we could say that this is a subspace of R2 by 2. So every real 2 by 2 matrix that we can construct, within that matrix space, within that vector space, we have a subspace here with this kind of condition. And that all of the conditions in a minute that we'll talk about are met. Just to give a couple of examples. And so he gives some more examples in the textbook that you can kind of take a look at that kind of make sense, specifically between vectors, but this idea that the vector space and ultimately the vector subspace has to contain the 0 vector, or at least the 0 matrix or the 0 as a component, and then everything else then has to stem from that, whether it's a line, a plane, a 3-dimensional within a greater dimensional space. Everything has to go through 0, and then any combinations we do has to maintain and be closed within that space. He gives, I think, some really interesting applications. For example, we talked about a specific kind of subspace, but you could say that an overall space as a matrix, a 3 by 3. So if we're to focus on a real matrix set that's 3 by 3, this would be a vector space. If you looked at all 8 rules, they would all be satisfied here. within this. So this makes overall a vector space. And something that you could check. All linear combinations would stay maintained. This includes the 0, so it would work. I think if we looked a little bit more in detail, and he asked this question, if I have invertible matrices, because I think it's kind of interesting to see when this stuff breaks more so than when it actually works. This is not a subspace, or sorry, not a space. I'll say not a vector space. And I'm going to leave kind of the reasoning up to you just to kind of verify, because there's also some questions a little bit later. But what I would encourage is think about if you were to find an inverse matrix and an inverse matrix, that if you added them together, can you create a matrix that's not invertible? And if we can do that, then that means this isn't a vector space. We don't have to worry about multiplying it by constants. We can just kind of focus on this and see, like, is this possible? And again, if we can come up with a matrix that's not invertible, then it's not a vector space and wouldn't be included. He goes in the next portion to talk about functions. If you're doing a college linear algebra course, then functions are important. Looking at which functions are in a space and which are not. He gives some examples there. Because this, again, is more so for a high school level linear algebra course, I'm not going to dive into functions or kind of showcase that. I'm mostly going to stick with vectors and matrices using real coefficients and focusing there. And so that's why I want to kind of get into the definition for the subspace, because I've kind of highlighted it, but I want to kind of formally write it up here. And then kind of talk through a couple of examples that he gives just to kind of give some background, because otherwise I think it's really clear in terms of the text as a resource for this. But if I want to define a subspace, we say that a subspace of a vector space, so a subspace of a vector space is a set of vectors. So again, this is why we can kind of think about it as a set and a subset, etc. It's a set of vectors that satisfies the following two requirements. And again, what's really nice about these two requirements, and what I've always tended to remember from this, is that they can be pretty much summed up in terms of the linear combination. But the first requirement is that if I do two vectors v plus w, this has to stay within the space. So if I do v plus w, then this is in the subspace. It's in the subspace. Just want to make sure I have the wording the same. And then the second requirement is that if I multiply my vector by a scalar, so again, c is some scalar, it can be positive, negative, or 0, then this is also still in the subspace. And you'll notice then, when we look at the full combinations, if I take any two vectors, v and w, that are in this set, and I combine them in terms of a linear combination, this has to be in the subspace. So we can sum it up by focusing strictly right here. But we have these two rules that kind of build up into that. And you see these also in terms of the 8 rules that are given at the beginning of the problem set. So this is our definition then for a subspace. So I like that what he gets, again, touches on in the next kind of piece is that based off of this, if we focus on R3, which is kind of where we've been a lot of the times dealing with vectors with 3 components, the space R3 is a subspace also. A space is also a subspace of itself, which kind of makes sense. It feels pretty trivial. It's like saying 0 is equal to 0. But it's true. This is a subspace of itself. R2 is a subspace of R3. R is a subspace of R3. And then just the point 0, 0, 0 is a subspace of R3. Now in each of these cases, what we have to make sure happens is that if I'm in R2, this has to include 0, 0, 0. If I'm in R, this has to include the point 0, 0, 0. Because again, this would be a line, this would be a plane when I'm in 3D space. This is just a single point. each time that has to be included, and it's because of the second rule. Right? The second rule says that if I multiply by a scalar, then this has to stay in the subspace. Well, C is 0. 0 has to be in the subspace. If you were just to draw any line that doesn't go through 0, then this isn't going to satisfy the definition and be a subspace for R3 because it would not pass through that 0, 0, 0 point. So just something to remember. The origin, 0, as well as these linear combinations has to be true. It's why I kind of like, in my head, I tend to always boil it down to this rule 3, and then trying to make sure and ensure that 0 is a part of it. So if we focused in R2, so if we kind of simplified this down a little bit, and then I'm going to work kind of with matrices next, just to kind of show some examples and the process that he explains, and just really expand on it a little bit. Expand, probably a better word. Let's say we were dealing with R2, and in the first example that he gives in R2 is breaking this plane, because this is really just the Cartesian coordinate system. We're really just working within the 4 quadrants. Is if we only focused on the first quadrant. So if I only took coordinates where x and y were both greater than 0. So if I only focused here, this would not be a subspace. And the reason why it would not be a subspace is that if I take these x and y coordinates, if I'm looking at that second rule that tells me that if I multiply by a scalar, which is cx and cy, both of these entries still need to be positive. Well, if C is less than 0, then this is not going to happen. This is not in the first quadrant. This would put me down here in the third quadrant. It doesn't keep me in the space. It's not closed under multiplication. So that means that if I focus just in quadrant 1, this is not a subspace of the entire R2. If, and in example 2, if I remember right in terms of his numbering, so if in example 2, he extends it to just the top 2, so what if we allow positive, and actually let me make sure that's the next one, because I want to say, include also, because I want to make sure I listed it right, because what he gets into next, and you could keep going, but if we did it, he said, all right, well, what if we included this and we included both being negative, right? So what if we satisfied this piece? So x and y are either both positive or x and y are both negative. If I take 2 coordinates from that, so let's say we took 2, 3, and then we took something like -3, -2. If I add these 2 things together, notice I'm not even multiplying by the scalar, but I'm working on that first rule there. Both of these satisfy. But if I add these 2 coordinates together, we're going to get something that's -1, +1, which doesn't fit our rule. Right, I've got 1 negative and 1 positive, aka this operation is finding me a point in quadrant 2, which is not in the original space that we're looking at. It doesn't keep me in the subspace. I was talking about the rule earlier. I was talking about the idea earlier that if you were to view your room as a space, now let's think about it as a subspace. If there's an action that we want to see and perform that takes you out of your room, then that action, that operation, or that action is in a subspace. Like it doesn't keep you in there if we essentially allow it. So that's why, again, these 2 coordinates, I think the examples he gives there are really nice. The other examples that he gives for a subspace are 2 very important types of matrices that we've seen a lot, really towards the end of the second chapter. Which is if you have upper triangular matrix, upper triangular matrices, this is a subspace of any Rn. Now he focuses on a 2x2, so if you let U be A, B, 0, and then C, for example, this is a subspace. The reason why it's a subspace is that if I multiply by a constant, then this stays upper triangular. Right? This would stay 0. All of these are still non-zeros, as long as C is not 0. Even if C is 0, then that's still technically upper triangular. Now, if I take any upper triangular matrix, so A, B, 0, C, and I add to it any other upper triangular matrix, D, E, 0, F, when I add these, A plus D, B plus E, 0, C and F, then this again would stay upper triangular because I would get a 0 and entries here. So again, I'm closed under addition and multiplication. Every linear combination of an upper triangular matrix stays upper triangular. Thus, this whole idea of being a subspace. We're not breaking out of the mold, as well as zeros are included. If you took a diagonal matrix, so if I have A, B, and 0, 0, then it's the same case. If I multiply by 0 or any other scalar, this would stay diagonal, because the whole definition is that I have entries here and zeros on the outside. If I do any kind of linear combination with diagonal matrices, again, we can show it really quickly here. If I take away those two entries, because we're just adding, no scalar is going to change that from being 0, then these entries will stay along the diagonal, resulting in a diagonal matrix. So therefore, this is also a subspace. And he gives a really interesting idea is that you can break it down even further, that a diagonal matrix is actually a subspace of every upper triangular. It's just the special case where B is 0. And that's kind of the idea. When you're working with this larger space, if we can carve out a smaller space on the inside, then that's a subspace. If you can keep carving, then a new subspace, a new subspace, a new subspace. The Russian doll effect, essentially. Just remember the one stipulation, that as we're drawing these smaller and smaller and smaller groupings, by definition, you have to include 0. Right? That origin point has to be included. We have to ensure that it's included as we're working through that. I'm trying to see if there's anything else. He leaves off, I think it's pretty self-explanatory. He leaves off before getting into the column space and the row space, which I'm going to save for part 2 for this lesson. Is the identity matrix. Is the identity matrix itself a subspace? Now, what's kind of interesting is identity matrix is a part of these two things, and an upper triangular and diagonal includes the identity matrix, but the identity matrix itself is not a subspace, because once I set this to be defined as 1, 1, 0, 0, remember that's that full definition. By multiplying by a scalar, we break that, right? It's no longer an identity matrix. And so it's really easy to kind of see how that fails. Now, in the part 2 for this, we'll start getting into column space, row space, and actually finish off this section. This section's really kind of an intro into those things, and then really introducing some terminology, what's called span, which I've actually mentioned towards the beginning. But hopefully this kind of helps, just kind of give a breakdown for, again, what a vector space is, what a subspace is, really kind of defined with the operations, this idea that you need to be closed under addition and multiplication, and looking at those linear combinations. Let me know if you have any questions, and take a look at the practice problems after looking at the second section if needed.